Hello students, so we are in lessons 2.5 and 2.6, and 2.5 and 2.6 both deal with exponential functions. So the purpose of this video is to make sure that you get a good understanding of what exponential functions are. So if we move on to the next slide, the very first slide gives us the definition of an exponential function, and the function looks like f of x is equal to a to the x. So this is unique because a lot of functions we've looked at, will be like a linear. So maybe you'll have 3x plus 1, or maybe you're dealing with something like a quadratic, and that's like 2x squared plus 3x plus 1. We may have even looked at a cubic function, so that might be like 5x to the third plus 6. What's interesting about all of these is that the value of your base is actually the variable. So quick little refresher, we know that when we say something like x to the second power, the x is called our base, and then the little 2 is called our exponent, right? So in all the equations we've ever looked at, our base was always the variable. But what's unique in this situation is if you look at what our function is, our exponential function, the base is a value or a number, and the variable is actually in the exponent. You'll see the line below it says a is any value greater than 0. And to further clarify that, a is allowed to be between 0 and 1, and then a is allowed to be bigger than 1. So those are the two options that you can have. Included in this, or I guess I should say not included, is the value 1. So if you go over here where I've drawn a star at the bottom under not exponential functions, having a base of 1 is not considered an exponential function because it doesn't matter what you plug in for x, it's just going to be 1. I could plug in x to be 1. If I do 1 to the first power, 1 to the 100th power, 1 to the millionth power, like all of those equal the same exact value. They're all equal to one another. So that's not really doing me any good. And so you can't include the value 1, but you can look at anything that's a fractional value between 0 and 1, and then anything that is bigger than 1. You see here that I've given you some examples of some exponential functions. So you can have a positive value as your base, you can have a fractional value, you can even have a radical value, and that's okay because it meets the conditions of where a has to be located. Not exponential functions on the other side would be something like x squared. Again, that's a quadratic function. The base is not a number. On the second one, notice the base is negative. That's not allowed, and then we've already talked about that last one. So how do you go and graph an exponential function? Well, graphing an exponential function is just like graphing a linear function. So let's do a little refresher for a second. Let's say I gave you the equation y equals 2x plus 1, and I say, hey, I want you to go graph this. Well, more than likely, many of you would make an XY table, and you would pick some random points, and you might say, you know what, I want to know when this is 0, 1, and 2. And so you would plug in 0 for x. 2 times 0 is 0 plus 1 is 1. 2 times 1 is 2 plus 1 is 3. 2 times 2 is 4 plus 1 is 5. And that would give you your coordinates, 0, 1, 1, 3, 2, 5. That you now could go and plot and put on a graph, right? Well, that's going to work absolutely no different for graphing a exponential function. I have 2 to the x, and so I want to plug in different values of x. So for example, 2 to the negative 3, or 2 to the negative 2, or 2 to the negative first, or 2 to the 0 power, or 2 to the first power, or 2 to the second power. And you see I have done all of these here. And what ends up happening is I get its corresponding y values when I actually solve those. Now I want to take a look at this one right here for a second. That is 2 to the 0 power equals 1. And this brings up an interesting property. I'm not sure if you guys recall it, but anything raised to the 0 power equals 1. And that's an important property that will come in handy. Okay? You can go ahead and look at the graph, and you see that this blue line, oh, let me not do that. Let's try that again. Sorry. Let's do the highlighter. You see this blue line here. This is representing the function I just graphed. So I got coordinates, I put them on my coordinate plane, and it produces the graph. On your own, you can pause this video and then look at letter B. There are two different types of situations. As you actually see in this graph right here, the blue line is going up on the right-hand side, whereas the other one looks like it's going down. And that's because there's two situations. There's something called an exponential growth, and then there's something called an exponential decay. So we're going to look at a growth first. An exponential growth says that the value of your base has to be bigger than 1. If that's the case, then your function is going to look something like this, where it is increasing exponentially. What it means when we say exponentially is it means that it is, in this case, growing extremely rapidly. So it kind of starts out slow, right? You can see these values over here. I'm going to draw arrows to it, right? They're all kind of very similar to one another. And then as soon as you hit about 11, there's a huge increase, right? They really, really quickly raise up in their value. So again, you're looking at that base value, and if the base value is bigger than 1, you automatically know you're dealing with a growth. Whereas with a decay, you're looking at the same thing, your base value, but the difference is if you're dealing with a fractional value that is between 0 and 1, you're dealing with an exponential decay. Now, don't get confused. A lot of people will see a b value equal to 4/2 and say, oh, that's a fraction. That means it's a decay. No, because you can evaluate 4 divided by 2, and that equals 2. And 2 is actually bigger than 1, so that would be an exponential growth. But if you were dealing with something like b is equal to 1/2, well, yes, now that is between 0 and 1, and that would represent a decay. Okay, when it's a decay, again, you notice that you're decreasing very rapidly. So you start out rapidly declining, and then you start evening out toward the end. You can see these points are kind of all very similar. This slide just kind of does a quick little overview again, that you can have an exponential growth, that you can have a decay. You can identify the domain and the range, which just means your x and y values. We have something called a horizontal asymptote. An asymptote is simply a line, or maybe it's the axis or an equation that your graph is approaching, but it never touches. And so the way that you can tell you have an asymptote, I'm going to actually make my highlighter just a little skinnier for you. Notice that on this value over here where I'm making my green, if you can see my green highlighter, notice that it is nearing my x-axis. I'm going to do the same thing on the other side. Notice that this side is also nearing my x-axis. It actually never touches. So although it's getting really close, it's never going to touch that axis. That is what a horizontal asymptote is. It means that your graph is approaching this line, or in this case the x-axis, but it's never actually going to touch it or intersect it. And that's what an asymptote is. We can have both vertical asymptotes and we can have horizontal asymptotes. So it just depends on the actual function. As you perform transformations and you move things around, that can determine if you'll have a horizontal or a vertical asymptote. You'll also notice on number 5 that I'm telling you that the function passes through the point 0, 1. This is for the parent function. The parent function means there's been no transformations that's been done to it, no movements of any sort, and so this is the main functions, the main parent functions pass through this point. That is not the case for every single function. I want to make it clear that you can absolutely move your exponential function, and you might have something that looks like this, right? So this is an exponential growth. It has a horizontal asymptote that's located over here, so that's a completely different value. Maybe that's y equals 3. I'm just making up something, versus my x-axis. Obviously, this is not going to go through the point 0, 1, because 0, 1 might be all the way over here. And that's okay. That doesn't mean that it's not an exponential function anymore. It still is. It just means it's not a parent function. It's been transformed. It's been moved. It's been shifted. It's been changed in its size. Okay? So I want you to think about some things in the real world that show an exponential growth or an exponential decay. There's actually a lot of different examples, a lot of things that we can think about that are really relevant to exponential functions. This is one of my favorite topics to talk about because people always ask me, well, why do I have to learn this? Why is this relevant? Well, again, because exponential functions, we don't live in a perfect world, and so exponential functions represent almost everything we do on a daily basis. So yeah, what I'm actually saying is math does relate to the real world. My favorite example of an exponential growth is using sneakers. If any of you enjoy sneakers, sneakers are seen as a collector item for some individuals, special type of sneakers. And I remember, I believe it was in 2008, if any of you are basketball fans, Ray Allen paired up with Michael Jordan and released what was called the Ray Allen 13s. It was a special retro edition of the Jordan Retro Collection, and it was a special edition of the actual shoe called the 13s. And when this shoe released, it was only released in select stores and select locations. I know for the East Coast, it was predominantly in the North that it was sold, and there was only a select number of shoes sold, and the shoe was selling for about $300, 300 something. By the end of the day, I went onto eBay, and the shoe was selling for over $1,000. That means with only a few hours, the price of the shoe, its value, increased tremendously. It went from being 300 something to being over 1,000 within just a few hours. That's an awesome example of exponential growth. Another great example is, unfortunately, due to the recent natural disasters and hurricanes, gas prices. Gas prices represented an exponential growth. It didn't consistently increase. It literally jumped from one price to another overnight because there was a lack of being able to get access to gas. So that also represents an exponential growth. A great example of exponential decay is your vehicle. As soon as you purchase a car and you drive it off the lot, it depreciates in value immediately, and it quickly loses value in those first couple of years. But once you think about having a car that's like 15, 16, 17, 18 years old, there's not much price difference in its value or its worth. If you sell your car at 15 years versus 18 years, you're probably going to get similar prices back for your car. And so that's a great example of an exponential decay, is how your car depreciates in value. So one thing that you might have to do is find the exponential function when given a graph. So I'm actually going to end this part of the video. This is going to be exponential functions part 1, and then I'm going to go ahead and start a new video for us to pick up and start talking about, okay, how are we actually going to utilize this? How do we write the equation when we're given the graph? And how can this be beneficial to us?